from Florida State University. And the topic of the presentation is applications of machine learning to nuclear theory.
Thank you very much, Oscar, and thank you all of you that have been so faithful to this and stayed here from Monday to Friday. It's been a long meeting, but it's been extraordinarily good. And of course, the first thing that I should do is really thank the organizers, because it's been a spectacular meeting, both from the scientific part and also because regardless of my age, when I go to a conference, I see new friends, I make new friends, I see old people. So just to give you proof that that's the case, so let me show you a couple of slides. Of course, this one we all recognize. That was the first picture that was taken yesterday. And then if you don't think I'm making good friends, this is perfect evidence. Who will trust you when you say, please eat a chapulín? But here's Nasser in that dinner that we have, and he was very happy to eat chapulines with me. Crickets, for those of you that don't know what chapulín means. And of course, everyone that speaks Spanish and got into a bus, we really got a kick of se prohíbe comer atún en la unidad, which translates into, please don't eat tuna in this unit. You can eat anything else, but please no tuna. So anyway, I mean, there is machine learning and stuff in my presentation, but I have to confess that comes at the end. We're all scientists here. We want to advance the science. So most of my presentation is going to be about the fascinating world of neutron stars, and particularly in this incredibly synergy that we have developed with many other fields. So as my colleagues from Europe, colleagues from the US, colleagues from Asia know, different societies across the world, we get together every decade or so, and we try to draft a document, which we call the long-range plan, to craft what is the mission of the field for the next 7 to 10 years. And that just happened in the US. And among the slides that we have here, there is one that I'm very proud of, which is called Heaven and Earth, which is trying to connect atomic nuclei to neutron stars. And I will explain how these objects, even though are intimately related, differ in size by 18 orders of magnitude. Yet what you measure in the lab has profound consequences to what you do in the neutron stars. So this is something that essentially I paraphrased in terms of, many of you probably have heard about the cosmic distance ladder. This is what cosmologists use, different techniques to be able to understand astrophysics, the distance to astrophysical objects. Here, what I did is I said, well, I also want to construct a ladder, but this ladder is going to be an equation of state ladder. No single method that you can see here will be able to describe the entire equation of state. So essentially, you build a ladder, and as you climb the ladder, you constrain the equation of state at different densities. So at the lowest densities, we have, for example, chiral effective field theory. And then one of the things that we do in the lab that I will spend some time is the neutron skin of nuclei. This is a purely nuclear experiment. And I will tell you how that impacts our understanding of the equation of state. We have heavy ion collisions and so on, until we get to the measurements, for example, using pulsar timing of the most massive neutron stars to date, which constrains the equation of states at the highest densities that we can probe. All this, of course, under the framework of multi-messenger astronomy. And let me tell you a little bit more about how are we going to get into the equation of state. So first, some explanations. So you probably heard at the beginning of this session that Alejandro Ayala was talking about the equation of state. It's a completely different regime. For example, relativistic heavy ion collisions try to probe the equation of state at very high temperature or very high excitation energies, but at very low baryon number. What we're trying to do is exactly going to the opposite direction. We want to understand basically what is the ground state of the system at a specific, in specific conditions, which means we're interested in the T equals 0, temperature equals 0 equation of state. So the equation of state for a system like nuclear physics, we have two flavors. We have protons and neutrons, or isospin. So essentially, the entire equation of state depends on the density of protons, the density of neutrons, or equivalently, you can say it depends on the total baryon density of the system and the difference between the neutrons and the protons, which we call the neutron-proton asymmetry. So if you calculate the energy per nucleon, which is what we call essentially the equation of state, you have it here. Then you have, again, I told you 2 species. So first you do it for symmetric nuclear matter. That means that you have a system, you put it in your favorite bucket to constrain the density, but you make sure that nucleons are equally divided. You have half of the number of protons, half of the number of neutrons. You turn off the Coulomb interaction, and what you get is this red curve. So this is the equation of state of symmetric nuclear matter. You see that it has a minimum. This minimum happens about 0.15 nucleons per Fermi cube. And what we call one of the critical phenomena in nuclear physics, we call saturation, is the fact that the slope over here is 0. So if you remember, if I take the energy per particle, take the derivative with respect to the baryon density, that is the pressure. So there is a pressure at which, there is a density at which the pressure vanishes. This is the favorite density. And if you look at heavy nuclei, you see that the interior is essentially nuclei at this particular density. Of course, you want to understand neutron stars, so you have to understand how much energetically you have to pay the price to turn protons into neutrons. Now, of course, protons and neutrons are both fermions. So if I remove protons from some level, I have to put them into a higher level because they're fermions and the previous levels are occupied. So this is a cost, and we label that cost as the symmetry energy. So what is exactly the symmetry energy? A very simple way to understand it is as follows. So you understand these very well, equal number of neutrons and protons. Let's go to the extreme case in which you have exactly the same bucket, same density, but instead of having equal number of neutrons and protons, you only have neutrons. So that we call the equation of pure neutron matter. The difference between the equation of pure neutron matter and the equation of symmetric nuclear matter, we call the symmetry energy. And the symmetry energy, as the equation of state of symmetric nuclear matter and pure neutron matter, depends on the density. So there are 2, it's a little bit of jargon, but let me define it. So this quantity here, the difference between the equation of state of pure neutron matter and symmetric nuclear matter, we call it J. But a quantity that is going to be more relevant is actually what is the slope. And the slope, remember, is the pressure. So that quantity, we call it L. So this is the pressure of a gas that is made exclusively out of neutrons. At the saturation density, this is the pressure that you can measure. And it's directly related to the saturation density, a trivial factor, and this quantity that I call L. So all you have to remember mostly for the rest of the talk is just one letter, and that letter is called L. So when you think about L, or I tell you about L, I'm telling you something about the pressure of pure neutron matter. A little bit more jargony, we say that the equation of state, or particularly the symmetry energy, is stiff if this L is large, namely the pressure is large, so neutrons are pushing very effectively against, let's say, surface tension in the nucleus. And of course, the opposite limit is soft, where the L is small. And the nice thing about nuclear physics is, of course, you have a connection between the micro world. So this is the microphysics that we do. And then this is the macrophysics that we try to calculate. We try to calculate, for example, the mass radius relations of neutron stars. You find a neutron star, you measure its mass, you measure its radius, and this is how you connect that. So you have an equation of state, you have a determination of the mass radius relation. Now, if I'm not mistaken, this is one of the very few presentations on neutron stars. So why are neutron stars part of the nuclear portfolio, right? You say, oh, neutron stars, these are these objects in the cosmos. They might have some relation with nuclear physics, but they might not be very interesting from the point of view of nuclear physics. So in this slide, what I want to convince you is exactly of the opposite. I want to convince you that nuclear physics is actually the predominant actor in trying to understand the microphysics of neutron stars. And for that, I'm just going to tell you the following, right? So you don't have to pay too much attention, but these are the equations that we need to solve to understand the mass radius relation of a neutron star. It's essentially hydrostatic equilibrium in Newtonian physics supplemented by some general relativistic correction. Now, if you solve these equations under the assumption that the relation from the pressure and the energy density is that from a purely fermionic gas, namely no interactions, the pressure is completely and absolutely determined by the Pauli exclusion principle. That is a calculation that was done in the 1930s by Oppenheimer and Volkov, and they made a very clear prediction. They say, if you have a neutron star in excess of 7/10 of a solar mass, then this degeneracy of the neutrons will not be able to support the star gravitational collapse, and you get a black hole. That's the number. As of today, we have several sources, several neutron stars we have exceed 2 solar masses. So then you ask, how do I get from here to here? What is the additional pressure support that I have to invoke in order to be able to satisfy that? And it's completely nuclear physics at short distances, right? So the interaction at high density or short distances becomes very repulsive. It's the repulsive interaction that provides the pressure support. So I like to say that this increase from 7/10 to 2 solar masses actually transfers ownership of the neutron star problems to this community, to all of us. So now what I want to do is, I don't want to claim that nuclear physics by itself can solve all these problems. And that's where the synergy that I mentioned at the beginning in this equation of state density ladder is going to come into play. And I'm going to go through some of the recent advances in chronological order. So you can see here 2017. And if you were paying attention, this is one of the most remarkable events that we have seen in this community. It is essentially the first direct detection of gravitational waves from the binary merger of neutron stars. So you have 2 neutron stars. They orbit each other. As they orbit, they emit gravitational waves. The emission of gravitational waves accelerates the collapse, and eventually they merge. Now, where is the sensitivity to the equation of state? So basically what happens is that if I have 2 neutron stars, let's talk about the right-hand side, the neutron star here is going to have some impact on the other neutron star through a tidal force, right? So tidal force, like the tides in the earth, is trying to dislodge or disturb or create actually a quadrupole moment in the companion star. If you are in a regime where things are linear, then essentially induces a response from the neutron star. So the tidal deformability was actually measured by the LIGO-Virgo collaboration. And they concluded that the equation of state is soft on the basis that they tell you if you have less compact stars, then you have an equation of state which is stiff. If you have one which has a low tidal deformability, then you have an equation of state which is soft. The nice thing about the tidal deformability is it's very sensitive to 2 fundamental parameters of the mass radius relation, which is the radius, the mass, and of course it has a very large lever arm because it's raised to the 5th power. So essentially, if you want just a cartoonish picture of what is LIGO trying to measure, the tidal polarizability essentially is measuring how fluffy the neutron star. If you have a given mass, and for that given mass, you have a very large radius, then that is very easy to polarize or deform. And that gives you, that is a stiff equation of state because the radius is large. So essentially, the tidal deformability is telling you about the fluffiness of the star. Okay, so this is one, 2017. Now we go to 2019. In 2019, we have the best measurement, most accurate measurement of the largest neutron star today. And that was done also in an extraordinarily interesting way, because in this case, what you have is an orbiting system One consisted of a neutron star, which the mass was determined to be significantly large. Another one was a white dwarf. So the nice thing about that is that if you remember Kepler's orbits, in particular the third law of Kepler, you remember that there is a universal relation with the cube of the semi-major axis and the square of the period. And that uniform relation is proportional to Newton's G times the sum of the orbiting objects. So if you're doing planetary science, then that's very nice because the mass of the light object, namely a planet, can be neglected. So this is a very accurate way, for example, to measure the mass of the sun. But what if the two objects have similar masses? Then classically, you're doomed, right? You cannot do anything else because the only thing that you can do is obtain the sum of the masses. But here comes a relativistic effect called Shapiro delay, which essentially is trying to obtain the dipole radiation emitted by the neutron star as the object rotates around each other. So imagine that you have here the neutron star. Neutron star is emitting some radiation. Here's the white dwarf star, and here's the observer. So as the light is emitted, the light actually has to dip and come out of the gravitational wave of the companion, so there is going to be a time delay. If you're in the opposite configuration, there is no delay, and that's essentially what Shapiro delay measures, and then you have here a very nice representation. So you need a general relativistic effect to break the degeneracy, and then you can figure out what is the Shapiro delay. Of course, it's proportional to the mass of the white dwarf. You extract the mass of the white dwarf, and then you come up with a very nice measurement with very nice precision of essentially the maximum mass of a neutron star that we have detected today. And unlike the equation of state suggested by LIGO, being able to support masses of neutron stars in this regime tells you that it has to be a stiff equation of state. Okay, so let me go on. I'm trying to go a little bit faster. There is another very nice observation. It's called the NICER. It's called NICER. Where am I going? So this is the NICER mission. It's this device, which is now living in the International Space Station. And the nice thing about the NICER is that also constrains the master radius of the neutron star. And it does it by something that looks essentially like science fiction. It actually looks in the back of the star. So how can you look in the back of the star? Well, the instrument is collecting photons. And as the star rotates, in particularly what we see as hotspots in the star, so NICER monitors the hotspots. As it rotates, it goes into the back of the instrument. Yet, because you have the bending of the light, which is another prediction of general relativity, you can see the back of the star. The more compact the object, the more you see. So essentially, NICER measures properties of neutron stars by looking into the back of the star. And they have provided very nice measurements. This is for the radius, and this is the star that I just described before. So we know, because of the Shapiro delay, very accurately the mass, and now we know the radius of the same object. There are two groups, one in the US and one in the Netherlands, and it also confirms that they favor a stiff equation of state. Okay, so now let me get to the laboratory. So now we are at Jefferson Lab, and what we have discovered for some time, and there is a very strong correlation between, remember this quantity L that I told you at the beginning, which is the pressure of pure neutron matter, and then the neutron skin of lead-208. So what is the neutron skin? So lead has 82 protons and it has 126 neutrons. So let's make a core which we have exactly 82 protons and 82 neutrons. So we know how to do that. The question is, where do we put the 44 excess neutrons? So the difference between the mean square radius of the neutron distribution relative to the proton distribution, that's the skin. So you take two radii, you take the difference, you get the skin. And the thing that we discovered, which is very interesting, is regardless of the model that you use, there is a very, very strong correlation between the pressure of pure neutron matter and the skin. So in this case, this pressure of pure neutron matter is pushing the neutrons in the skin against surface tension. If L is large, you make a big skin. If L is small, then you make a small skin. How does that translate to a neutron star? Well, it's the same L, the same pressure of pure neutron matter that determines the radius of a neutron star. And then you see here, for example, for a low mass neutron star of, let's say, 0.8 solar masses, that the correlation is also very, very strong. So the beauty of the experiment that it has been conducted at Jefferson Lab is that you make a measurement at the femtometer level, and then you make a determination of the size of the equation of the neutron star, which is at the kilometer level. So you go 18 orders of magnitude, yet the same quantity, L, is determining both. So the experiment has been done. And then how does the experiment work? So basically what you're going to measure is a quantity that will be zero if parity will be a good quantum number. But we know that the weak interaction violates parity. So they do a parity violating experiment, which is essentially counting the number of electrons that scatter to the right, the number of right-handed electrons relative to the same number of left-handed electrons. So these electrons are polarized in the direction of the motion. These electrons are polarized in opposite to the direction of motion. And then you just measure the difference relative to the sum. And again, if the weak interaction will preserve parity, this quantity will be zero, but it doesn't. So basically what you're measuring is the interference between the normal one photon exchange and the interference with the Z0 exchange. So this is electromagnetism, and this is weak interaction via the Z0. And what we want to measure is something related to the neutrons. So here in the denominator, you have the charge form factor, or call it the charge density of lead-208 that has been known for a long, long time. What we want to extract is the weak form factor, which is dominated by the neutrons. You take its Fourier transform, and then you know the neutron density. And what I want to emphasize is that this is a purely electroweak measurement, right? So no hadronic distortions, no hadronic uncertainties, purely electroweak. And the reason that this experiment is so compelling is because the photon couples to the up and down quark in a very trivial way. If you add the charges, you get +1 for the proton and 0 for the neutron. The weak charges, namely the coupling to the Z0, are almost opposite. So you get the 1/3 here and you get the -2/3 here. So now Z0s are essentially blind to protons, but they couple very strongly to the neutrons. So that's the motivation for the experiment. The experiment has been done, and here is the answer. So what Piekarewicz measured, this experiment at Jefferson Lab, was a neutron skin in lead of 0.29 plus or minus 0.07 Fermis. Relative to some predictions and some experiments, this is very, very large. Unreasonably large in the eyes of some people that believe that the skin has to be small. But as I was trying to tell you, the fact that the Piekarewicz experiment is purely electroweak means that the experiment is dominated by statistical uncertainties and not systematic. So the systematic uncertainties are completely under control, and they suggest that we have a very stiff equation of state at the densities that can be probed by these experiments. Now, some of my colleagues have said, oh, maybe this is a fluctuation. So our colleagues at Mainz are building a beautiful, a new facility called MESA. And the hope is that the same experiment that was done at Jefferson Lab with this kind of uncertainty will be repeated at the MESA facility in Mainz, and they will be able to reduce the uncertainty by at least a factor of 2. So a picture is starting to emerge. So again, let me try to tell you what happens if we follow this equation of state density ladder. So the Piekarewicz experiment measures the equation of states at densities that are accessible in the lab. So for example, these are densities that you can see in the interior of a nucleus like lead. Gravitational waves are sensitive to about 2 times nuclear saturation density. And of course, I told you that heavy pulsars at much higher density. So if it is true, and of course there is a big if, that laboratory experiments suggest a stiff equation of state, followed by gravitational wave, which suggests the opposite, a soft equation of state, but ultimately a stiff equation of state, because there is no way that you can explain two solar masses without a stiff equation of state. There is a very exciting possibility that this transition from stiff to soft, basic to back to stiff, might be actually an indication of a possible phase transition. This is the nicer data. This is the two-star. Remember, there is a two solar mass limit. This is another nicer measurement. And these are some of the calculations that we've been making. So I like, in honor of my birth country, which is Mexico, you probably remember that there used to be a lot of Volkswagen Beetle going through here. So this I call my VW Beetle equation of state. Because look, it's exactly the same form. Okay, so that's the physics. I hope I convince you that there is an incredibly interesting synergy between fields going from gravitational waves to nuclear physics to particle physics. And then in the last few minutes, I want to tell you a little bit about where is machine learning coming into play. So the first thing that I want to tell you is about the outer crust of a neutron star. So the outer crust of a neutron star is a very non-homogeneous system, which essentially all that you have is individual nuclei, well separated. So the only interaction between these nuclei is the Coulomb interaction. So believe it or not, what they make in the crust of a neutron star is a crystal of neutron-rich nuclei. And as the density increases, the relevant nuclei go from essentially the region over here, which we know very well, the iron-nickel region. And then we go to the region of n equals 50, right? So magic number n. And then most of the nuclei in this region are well known. I mean, you can see here that we have nickel 78, which of course has been a great success of the community. But then as the density increases, then what becomes favorable is the n equals 82. And what you need to understand is what are the masses of nuclei over here. From the region of what we know to the region that we do not know, it's enormous. So there is no other way to try to compute theoretically what are the masses relevant for the outer crust. So like Vera yesterday, I also had a simulation and it also didn't work. But if I would run the simulation, you will see, this is for the R process, you will see some seed nuclei that capture neutrons very, very, very rapidly and actually populate the neutron drip line. Then they get to these waiting points, and then they go back to equilibrium, back to stability. So again, for these two things, you will need masses in regions that they are not accessible by experiment. So what we did is we constructed a Bayesian neural network where we try to put as much physics as we can and let the machine do the rest. If I remember correctly, I think it was Roelof at one point when we were talking about masses, that he was saying, okay, all models agree in the region that we know, and they violently disagree in the region that we do not know. So what did we do? Okay, so use your favorite nuclear mass model. So it can be density functional theory, which we advocate, or it can be any mass model, micro, macro, whatever you want. So for example, we also use this Duflo-Zucker. Now, what we do is we construct the residuals between the theoretical prediction and the actual experiment. So this is here the residuals. And then we train a neural network to work on the residuals. So what's Feynman doing in all of here? Well, first of all, he's my favorite physicist of all time. So the spirit of what we're doing is the following. Here is Richard Feynman, a faithful picture of Feynman. Here is our DFT or mass model calculation. So we get a very good idea by using nuclear models for what the masses should be, and then we let the difference between the two be refined by the artificial neural network to discover this. And then one of the things that we were very happy is at the time we trained with the atomic mass evaluation 2012, and then we predicted some of the masses. They came back and then we agreed. Not only do we agree, but I think the most important aspect is that because it's a Bayesian approach, we're not only giving you the central value, we're also giving you error. So this is a nice example to calculate masses in regions that we don't know, but it's an extrapolation, right? And as this fellow says, at this rate, this lady is gonna have about 40 husbands in about a month. So extrapolations are extraordinarily hard. So of course, the success that we have is just by going a few nuclei away from where data is available. Okay, so then the other thing that we do is we have models. And in those models, I don't want to explain these. There are lots of coupling constants. We try to understand the behavior of finite nuclei and neutron stars with the same model. So these parameters have to be calibrated to many amounts of data, finite nuclei properties, neutron star properties. So then we do essentially Bayesian inference of model parameters. We try to compute the model parameters. And then also what is very nice is you can find out what is the uncertainty in the particular observables that you have. And then you can say, well, if the uncertainty is large, can I actually predict what experiment should we do to reduce the uncertainty? And that you can do with correlations, right? So for example, if I see that this parameter L, that I already showed you many times, is purely determined, I can find the correlation with the neutron skin. I will discover a very strong correlation. I will go to my experimental friends and tell them, can you measure the neutron skin of Leto rate? Now, what happens here is that it's extraordinarily expensive to calibrate these models. So let me go essentially to my last slide. So I'm not going to explain very much, but if people are interested, we're calculating now emulators. So let me just read you what an emulator is. They're statistical machine learning models that faithfully reproduce the behavior of a complex physical system at a tiny fraction of the computational cost. So what you do is you take a model that takes a long time to run. You run it for specific cases, that is your training points. You train with these points, and then you construct an emulator that faithfully reproduces the results, but at a very small cost in computation. Okay, so let me just conclude. Of course, I have to conclude by showing you all the people that have been instrumental in doing this research, many collaborators that I've been, of course, enormously grateful. And of course, I have generations of older students and students that are coming. Now they're graduating, and eventually the chain continues. So just to tell you, if you want to see a time evolution of the Hamiltonian, here it is. I did graduated from, if you remember at the very end of the tour, we went to the old Facultad de Ciencias. That's where I graduated. It was 1981. Now run the simulation a few years later. This is what you get. So that's a perfect time evolution. And I thank you very much for your attention.
Thank you, Jorge, for this wonderful talk. Are there questions?
Thank you, Jorge. Very nice talk and summary. I was wondering, with your equation of state, well, what you conjecture, stiff, soft, stiff, what are the consequences for the speed of sound? In other words, you know that there is this conformal limit, and do you go above for normal density or relatively low densities? What do you get?
So let me see, because I think I removed that one. Yeah, so basically what you have to do, and this is Alejandro's question, is if you take the derivative of the pressure with respect to the energy density, you get the square of the speed of sound relative to the square of the speed of light. And there is a conjecture, which is based on conformal field theory, that ratio should remain below 1/3. That is heavily broken for us. And it's heavily broken at relatively low densities. And it's just because of having to reproduce heavy neutron stars. So we haven't gone because we don't have the reliability to go to an enormous large density to recover the conformal limit, but we go way above the conformal limit. Yeah.
But physically, that should have consequences, right? So what observable would you link to this violation of conformal limit?
I mean, I think radii and masses, right? Radii and masses. Those are the ones that are responsible for the stiffening that go above the conformal limit. And I think that if you want to enforce a equation of state that actually satisfies the conformal limit, is very hard. Maybe you'll need very strong phase transitions or something. We don't have any phase transition at the moment. So for us, it's inevitable to violate the conformal limit.
Thank you for this nice talk, relating all the fields of physics together. I had a question about the last part of your talk, which is the usage of the machine learning to predict things. I mean, if you put the picture back where the models actually are all acting widely outside the region, right? This model. And, you know, when we discuss it also, I always tell my graduate students, machine learning does nothing that you cannot do yourself. It just does it much faster and it has a lot of database. Yeah. So if I look at such a picture where the models are all going all over the place, I cannot imagine that the machine learning can then predict something which is better than this. What am I missing in your discussion?
You mean better than the very large uncertainty?
Right. So I want to get out of the I want to extrapolate, of course. Yes. And I see this is the extrapolation. I see it with my own eyes. And I then say, there's no machine learning that can do better than my eyes.
Yeah. So I think that where we win, of course, you have to understand that probably only one of those models that is shown here might be Duflo-Zucker, right? So we are biased here that we use Duflo-Zucker. Now, there are a couple of things. First of all, we don't go very, very far away from here because we don't extrapolate well. The other thing that we do is we put the error bars. So at least the error bars are giving me some sense of how away I'm going to doing the extrapolation, because there is a very strong correlation. If you go very close to where there is data, the error bars are small, as you might imagine, if you go far. The other thing that we did is we did not limit ourselves to Duflo-Zucker. So what I can say is that with these models, refining them with the Bayesian, and remember, it's just the refinement, right? So the central values change, and I want to understand only the difference. Then if you're too low, you go up, and if you're too high, you go down. So there is help from the machine learning because it does learn some of these patterns, but I couldn't emphasize more that this is a very bad way of trying to go to very large differences from the region where you come.
Okay, so the error bar is really a reflection of how wide these models are deviating from each other.
So this is the reflection of one single model captured by the Bayesian neural network. But if you look at the other models, which we have done, then the error bars do not increase very much.
Okay.
So I would call this that you're looking at really the statistical error of the Bayesian neural network, whereas that I will call the systematic error of models.
Thank you.
Here. Hi, thank you for a very nice talk. So I have a very, very short comment and then a question. The comment is related to Alejandro's question. And the thing that you have this violation of conformal behavior in the sound velocity is okay, right? You're going to recover the right behavior when you go to perturbative QCD, right? So you have this peak, which is going to go down, and then it's going to be conformal again. So I see no problem with that.
That's right, that's right. The only thing is that, of course, when people conjecture it, they say we're going to be below the conformal limit forever, but it's not. Now, we have not done the perturbative QCD calculation, but other people do, and then, of course, you recover the limit. Now, how to match them, it's interesting.
Exactly. The question is if it's coming from above or below, and there's still a discussion, sure, but you're going to recover it. And the question would be the following. So you argue that you have this soft, stiff behavior that you argue that could be a good
justification for a first order phase transition to be present there.
Indication.
Indication, yeah, of course. But then that would also open up the possibility for a twin star scenario where you could have very different radii for the stars. So I'd like to have your comment on this possibility.
I wish I could comment because I haven't done anything, so I cannot comment. I cannot give you a reliable comment. But I mean, I think, as you can imagine, right? I mean, trying to see if there is truly a phase transition is very speculative. So at this moment, we're waiting for the improvements in many fields. They're going to be improving in nuclear physics. There are going to be improvements in gravitational wave detection and so on. But I think it would be very interesting if there is actually a phase transition, but we haven't looking at the possibility of the twin stars.
If the chair allows me a quick question. So, I mean, this dispersion that you have there, can it be made better if you use constraints coming from perturbative QCD?
You mean now for the equation of state?
Yeah.
Okay, so this can be a very long discussion because perturbative QCD, according to the practitioners, requires a density of at least 40 times nuclear saturation.
That's correct, but you can use this to constrain the
You can use it.
anyhow. Yeah.
So then some of our colleagues from Europe actually have created a little applet that you can plug into your equation of state, and they're going to tell you if it's consistent or not. And because our equations of states are so constrained by finite nuclei and neutron stars, we have never violated that. So for some very exotic equation of state, I think the PQCD might be of relevance, but in our case, we haven't seen it.
Okay, thank you.
Okay, thank you. Are there other questions or comments? So if not, let's thank Jorge again.
There's one here.
And well, sorry? So we move on. And our next speaker is Andrea Delgado from National Lab. And the topic will be quantum frontiers in nuclear physics, unleashing precision through quantum computing.
I would like to start my talk by thanking the organizers. This is the first time that I attend this meeting, and full disclaimer, my background is actually high energy physics, so thank you for the community for welcoming. And I think a lot of the applications that I will talk about today have some sort of application in nuclear physics as well, so I will try to make the connection where possible. So another Oak Ridge talk. I would like to also start by motivating a little bit why we think quantum computing might be useful in these fields. So if we think about the experimental, especially high energy physics program, we have these large scale experiments like the LHC, like all of these underground neutrino experiments that not only require a lot of scientists to operate, but also they produce large amounts of data. So specifically the LHC experiments are just generating more and more data that is posing a challenge to conventional computing techniques. And also most of the systems that we study are actually quantum in nature. So if we study, for example, quarks and gluons, the previous talked about the equation of state. So all of these systems are quantum mechanical in nature. And even for powerful computers like Frontier, like the supercomputer that we house at Oak Ridge, 25% of the node hours that are allocated at Frontier and also Aurora at Argonne are actually allocated to lattice QCD calculations. So these calculations are very expensive. And then comes Feynman about 40 years ago and says, why don't we use actually quantum systems to study another quantum system? And I think this is a very powerful idea, but it's actually something that it's really hard to make happen in practice. So why do I say it's something challenging? Of course, if we use qubits, which are the quantum version of bits, the classical information processing element, we get an exponentially large Hilbert space that we can use to encode and process information. But the true power of quantum computing comes from entangling qubits. So you have to be very smart about how you can entangle these qubits. And of course, you have superposition from quantum mechanics, and you can explore many options at the same time in some way. But you also have to be very smart about how you extract information from the quantum world. So it's actually not an easy task. So quantum computing is an emerging field that has found many applications, not only in the scientific field, but also in the commercial field. There's applications in finance, for example. But if we were to break down what kind of problems we can solve with quantum computers, or what kind of problems we think quantum computers are good at, we could basically see that most of these applications fall into this list. So as I mentioned, quantum computers are really good for simulating quantum systems. They're very good at function inversion, combinatorial optimization, sampling complex distributions, because it's really easy for quantum computers to generate new statistics. And also for solving linear systems. So this is actually the core of Hamiltonian simulation, if you want to find like the eigenvalue of a Hamiltonian or an operator, and also for machine learning, because basically you're doing big, function fitting with matrix multiplication. And before I move on into the applications, I will also like to mention that quantum computing is only a subfield of this big field that is called quantum information science. And inside quantum information science, there's other more practical applications, like using quantum mechanics for quantum networks, the quantum internet. There's a lot of work in quantum sensing as well. There was a talk on Tuesday by Ronald. And of course, this quantum computer. And for this talk, I will focus on two specific applications of quantum computer, which is simulate physical processes and also accelerate the information processing by using quantum machine learning or quantum enhanced machine learning. So what does it mean, or what does it look like to work on quantum computing, on quantum machine learning applications in this era? So we usually refer in the community as the NISQ era, is noisy intermediate scale quantum computer. And these devices are characterized by having only a handful of qubits, usually in these stations in the order of 100 qubits. But these qubits are also noisy, so it's really hard to extract useful information from these devices. There's a lot of applications that have been developed, and I think this is basically motivated by a lot of tools that have been developed by the big companies, which have enabled the easy adoption of all of these techniques. And most of the hardware that we have access right now is cloud-based. So you create an account and then you submit a batch of jobs or tasks that you want to perform over the cloud, and then you get your information back. And a lot of the applications that you will see today in the literature are actually a hybrid framework. So you usually have some computation that runs on the quantum processor, and then some subtask that runs on a classical computer. So it wouldn't be an Oak Ridge talk if I didn't talk about what we do, and some highlights of the things that we're working on. So we work on the simulation of quantum systems, of course, machine learning, but we also work on developing a lot of software libraries that the public can use. They're open source. For example, tensor networks, compilers, if you have, for example, tasks that you want to run on several backends and you want to compare them. We have a software for that. Some colleagues of mine work on the first simulation of a nuclear system. So they did a calculation of the deuterium. And also we're working on the actual integration of high performance computing. So we want to plug in the power that we have from Frontier, for example, with a quantum computer. And now moving on to the applications to high energy physics and nuclear physics, I will talk today about two main topics. So the first one is quantum enhanced machine learning and also field theory simulation. So I will highlight some a few examples of applications, but if you want to dive deeper into what kind of things we can do with quantum computers, I will refer you to all of these reviews. And more recently, there was a meeting at CERN where we actually collaborated with IBM to think about what kind of problems we can solve once they have hardware that is more than 500 qubits or something. So thinking about the future, this is also a really nice review. So the first topic is how we can accelerate information processing with quantum machine learning. So quantum machine learning is basically the combination of the processing power that we have from quantum computing with the power of classical machine learning, which basically fitting functions over a large feature hyperparameter space. And by combining these two fields, we hope to solve these kinds of problems, which are basically the ones that we solve with classical machine learning. But we hope to do so using fewer data, less computation time, and hopefully less parameters. So one of the first questions that I always get is, how do these quantum machine learning models look like? How are they different from a classical neural network? So I always like to show this picture. So we have a classical neural network, and this is what a quantum neural network looks like. So we have some input data that we want to process, usually classical data. And then we have our neural networks that is composed of neurons and then some weights that that we train or that we optimize towards a particular task. So if you want to do inference, if you want to generate new samples, or depending on the task that you're targeting, you optimize those parameters. So for the quantum neural network, we have exactly the same components, but then instead of having the neurons and weights, we have our qubits, which we usually start or prepare in a state that we know, usually either like up or down, for example. And then we have a series of gates that are the operations that you can apply to the qubit. So basically, if you start from a quantum state that is pointing up, for example, you can use a rotational gate to rotate that quantum state into the Hilbert space. And those parameters are also tunable. So in the same way that in classical machine learning, we optimize those parameters for a task, the same way in the quantum machine learning model. We also have gates that entangle the qubits. So that's how we get this exponential power for computation. And then the next question is, why do we care about quantum machine learning if we already have classical neural networks that are pretty good at feeding data, and extrapolating to regions where we don't have data? Why quantum machine learning? So there's a very simple explanation for that, and I always like to compare this to the classical machine learning model. So if you're familiar with support vector machines, which is a very typical machine learning for classifying data, support vector machines are based on a trick that is usually referred to as the kernel trick, and it works the following way. So if you have some sort of two-dimensional data and you have two classes, like cards and stars, for example, if you wanted to find a function that will give you some separation so that you can say like upwards of this line or this classification, it's hearts, and then down will be stars. It will be really hard to find such function. And if you find it, it will probably be very specific to this data. And if you were to give it new data, then it will not generalize well. But it turns out that if you enhance your data and you elevate it to, for example, a 3-dimensional space, it might be the case that you find a 2-dimensional place where you can find a perfect or nearly perfect separation. So this is basically the so-called kernel trick. If you use that feature space and you take the dot product, it will tell you how similar two points are. And that will allow you to find this boundary decision line. In quantum machine learning, we are basically applying this kernel trick because we are encoding our classical information into the Hilbert space. Now, the caveat here is that we have to access this information via measurements. And then in the classical machine learning world, you just have to compute the kernel. But then the power of quantum computer comes from the fact that there are some feature maps that are really hard for classical computers to compute. So by using these quantum enhanced models, we expect to gain this power of classification. So that's one application. Another application, I already told you about how it's really easy for quantum computers to generate new samples by a fraction of the cost that it will take to classical machine learning models. So one of or another application of these quantum computers is to actually model distributions, which we do very often in high energy nuclear physics, where we have our Monte Carlo and then we generate our data. So there's a model that is called a quantum circuit Bohr machine, and it's referred as QCBM basically because by applying the Bohr rule, by taking the expectation value of a quantum state that you prepare, you can generate new statistics. So in this case, we take, again, our neural network, and then we take measurements in a given basis, usually the policy basis, and then we can populate a probability distribution. So we train this model by actually using a classical optimizer, just in a classical machine learning model. So for example, we can start by preparing a state that populates a random distribution, and then by taking a loss function between that populated distribution and our target distribution, we can actually train the model to learn a given distribution. So how do we construct these distributions and encode them into a circuit? So if you think about when you couple several qubits together, you have the basis state. So if you have the qubits, then you have the 0, 0, 0, 1, 1, 0, and 1, 1. So we use those as bins for our distribution that we're trying to learn. And then the amplitudes are the amplitudes of the quantum state. So we found that by training this model, we can actually reproduce the statistics of kinematic distributions in a typical LHC experiment, actually pretty good. But what was interesting was that the model was also able to learn the correlation between the distributions, not only the marginal distributions. So we were able to actually capture the physics of the process that was the underlying process of the training data that we were using. Just to conclude this section, some comments on quantum machine learning with not particular emphasis in high energy and in nuclear physics applications, but in general. I think there's still a lot of work to do in terms of characterizing these models. We still don't understand quite why they work pretty well. But there are some tools that we can borrow from classical machine learning to understand features like generalization, like overfitting, for example, and also some tools from quantum information theory, such as the quantum feature information, the capacity of the model, for example. And the current paradigm for quantum machine learning is that these models are actually pretty expensive to train. So usually we train them classically, and then the power comes from actually running the trained model. And I think an interesting applications for this quantum machine learning models is to process quantum data. So for example, if we have a quantum sensor or some sort of quantum system that we want to study. And also maybe combining these quantum machine learning models with HPC techniques. So I talked about also how we can couple these models for quantum sensors, and I think this is an interesting application specifically for our field because there's a lot of development currently in using quantum sensors for detecting physics beyond the standard model, for detecting new interactions. So if we can couple some of these new experiments and techniques with quantum machine learning models, I think it will be an interesting avenue for our field. Now to the last section of my talk, simulating quantum physical processes. So simulating a quantum system with a digital quantum computers, because there's several kinds of these devices, involves basically 3 steps. So we have state preparation. So we have our physical model that we're interested in simulating. And then we have to map this system into the degrees of freedom of the quantum computer. Then we can perform dynamic evolution by using unitary matrices. So usually this process involves a technique called totalization, where you take your unitary matrices and then partition it to evolve it in time. And then you have to figure out a smart way for extracting information from the quantum system that you prepare. So finding an observable of interest, or maybe some expectation value of that operator. So as an example of this application, I'm gonna briefly describe how to do the simulation of the Schwinger model, which is or has become a benchmark for quantum computing applications. Because it has several similarities with QCD, which will be eventually the target for this kind of applications. It has several features that make it very similar to QCD. And then it has a Hamiltonian that has this form in a discrete version after using a staggered fermion formulation. So basically for a small Schwinger model, this is how it would look like. Then we have to actually map the qubits to the degrees of freedom of the Hamiltonian to the qubits. And there are several ways to do that. One, or the most popular one, is the Jordan-Wigner transformation. Another one is the Kogatsuskin formulation. And then after using this transformation, our Hamiltonian looks basically like this. So then we can construct a quantum circuit just like the one I've been showing you to evolve an initial state, usually say all qubits in 0, an entangled state, and then you can evolve that initial known state to a desired state of the Hamiltonian. Then there are several ways to construct this state. One of them is adiabatic state preparation. And the most popular one is the variation of quantum eigensolvers. So this is another hybrid technique where you prepare your circuit, take an expectation value of some sort of operator. In this case, it could be your Hamiltonian, so that you find the ground state of that Hamiltonian, and then you optimize the parameters of this circuit classically. So another question I always get is, are we there yet? Can we extract meaningful information from these systems? And the answer is we're not quite there yet. to perform the simulation, there's a lot of resources that are needed from these quantum devices, and there's a lot of technical limitations. So for example, for the Jordan-Wigner transformation, if you want to do a simulation with only 4 sites, which is a very modest system size, we need 4 qubits for the fermionic operator, 1 qubit per link. So that means we need 8 qubits in total. So that is a transformation that is just not scalable given the constraints of the current device. To simulate dynamics, we need this process called trotterization, which involve a lot of operations that go beyond the coherent time that we have from disentangled systems. So it's usually unfeasible on current devices. And then for state preparation, if you would want to do adiabatic state preparation, you run into the trotterization problem as well. And then for BQE, you actually need a lot of measurements, a lot of executions of your circuit to train or to update the parameters of your quantum circuit. So it's really hard. But I think there are many techniques that we can apply from nuclear physics. So the question becomes sort of the opposite, not what can quantum computing do for nuclear physics, but what can nuclear physics do for quantum computing? And some examples of these are constructing circuits or ansatz that are inspired by the physics in the system. So the chemistry community came up with a unitary version of the coupled cluster that is suitable for running quantum devices. And then there's an interesting recent application of using a mean field approximation for simulating large systems, where instead of simulating, for example, 6 qubits like we have here, we could simulate a Hamiltonian for 3 qubits and then use an approximation term for the Hamiltonian and using and getting the contribution from these 3 other qubits as an approximation to the Hamiltonian. So in summary of my talk, I hope I convinced you that there are several promising applications of this emerging field to nuclear and high energy physics. There's a lot of applications that I didn't mention today. There's been a lot of work in exploring applications for lattice QCD, nuclear structure, effective field theory, and a lot of applications for data analysis. There are many challenges that still exist related to hardware. There's a lot of qubits and gates operations that we require to perform these simulations. And then there's also the issue of noise. There's lots of techniques that are not scalable right now that I didn't talk about today, but that's still an issue. And I think from the point of view of the nuclear physics community, there's a lot of things that we can contribute to developing algorithms that are efficient and that can be run on near-term devices to bridge this gap between what currently available hardware we have right now and actual applications that are useful for our field. And there's also a lot of work right now into combining or integrating HPC resources with quantum processors, so offloading parts of these algorithms to each one of these processors and combine the power of these 2 computational paradigms. So with that, I conclude my talk, and I'm happy to take any questions.
Okay, thank you, Andrea, for this nice talk. Are there questions or comments?
Thank you for this very nice talk. I have one question concerning the quantum machine learning part. The mathematical algorithmic that you are using are, as far as I understand, are essentially the same that are using the classical part, isn't it?
Yes, so in classical machine learning, there's this theorem that largely enough, a neural network could be a universal function approximator. So there's a similar way to prove that these quantum circuits, if they are deep enough, they can actually explore the full Hilbert space if you want to parameterize a function.
I have a second question concerning the nuclear physics application. According to your knowledge, is there nowadays a case in which really you can perform a nuclear calculation that is not affordable with a classical computer? Not really, because this is my impression.
Yeah, not yet. There are prospects specifically for lattice QCD, but I think there's been some work on simulating SU2 theories, but that's the closest that people have gotten to QCD. And the largest simulation is of 50 lattice sites, so it's not comparable to classical calculations.
Okay, thank you.
There was a question first there, Osvaldo.
Thank you very much, and excuse me for my ignorance. I mean, one thing is quantum computing, and the other is the quantum description of a system. So the moment you try to fix your knowledge, the wave function will collapse. If the wave function collapses, then you cannot get any more information. So how you treat then the time evolution of the system is not a purely statistical concept.
Sure. For the case of quantum simulation, for example, if you want to do simulation, you can build an operator, for example, to extract the ground state or, for example, the magnetization, if you're using to simulate like strongly correlated systems. So you can find ways to construct operators so that once you collapse the wave function, it gives you meaningful information. But yes, that's one of the caveats. You don't get access to all of the information that's encoded on the Hilbert space.
No, but it's exactly what Feynman was telling. I mean, perhaps quantum mechanics cannot be the ultimate theory of nature, although the system is quantum. Therefore, if I base my information on the wave function, and I want to qualify the wave function, then that wave function will collapse the moment I get information from it. But the system will continue with evolution, so that's a problem. In other words, they should be time dependent, not only configurational dependent. And the two things are different.
Okay, thank you for the comment. Moshe?
Thank you for a very nice talk, very optimistic. Can you summarize for us in broad terms, not going into many details, what needs to be achieved? Don't care how long, but what needs to be achieved for me to have quantum computers on my desk?
I think I will answer with a question. Why would you want to have a computer in your desk?
Very good. So, thank you. Are there other questions or comments? This paper. Yeah. A simple question. Can one at this point talk about the cost of this thing? How would a computer of this level compare, a regular computer of this level compare with this computer, and is there an evolution on this?
So that's a great question. I don't have the answer now, but I'm actually working on a project where the Department of Energy is trying to figure out or to put a dollar value of buying a quantum computer compared to running, for example, Frontier. But it's a difficult problem because there are no well-defined metrics to say this is where the quantum computer excels, because there are currently not many applications that are fully quantum. So for example, for training these circuits, you need to offload the optimization of the parameters to a classical computer. So what the approach that we're taking now is to say, if we take, for example, the problem of Hamiltonian evolution, can we offload the state preparation to a classical device? And if we can do, I don't know, like the time evolution on a quantum computer, how much will we gain in terms of like resources and I guess the cost of operating Frontier, for example, if we use or if we bought a quantum computer. But it's a difficult question finding those parameters and putting a dollar value to these devices.
Okay, thanks. Other questions or comments? I don't see any, so if not, then let's thank Andrea